So in that case, let me go on and describe the Aharonov-Bohm effect. So Bohm was a very famous physicist. He was also a philosopher. Bohm actually discovered in an independent formulation of quantum mechanics, which is known as the pilot wave theory. Okay? Bohm discovered a different formulation of quantum mechanics known as the pilot wave theory. And this is what is known as a quantum theory with a hidden variable theory. They are not the mainstream interpretation. They have hidden variables. But unlike Einstein always believed that quantum mechanics should have hidden variable because he didn't believe in the EPR effect and the spooky action at a distance effect that comes from entanglement. But what Bohm showed that, yes, you can have a theory with hidden variables, but it'll be non-local. So particles can still talk to each other faster than the speed of light. So yeah, something has to give. Okay, but that's not really why we are here. We are here to discuss the Aharonov-Bohm effect. So what is the setup for the Aharonov-Bohm effect? So suppose we consider electrons in a region A. So we have some region, say called region A, and we have this is the source region. And what happens is that there is another region called region B, and this is the interference region. And in between these two regions, there is some sort of barrier. And the barrier has two slits. So the electron, can go from region A to region B, but it must travel via these slits. Now, behind the barrier, suppose that we have an impenetrable cylinder. So this is an impenetrable cylinder. So we are looking at it from above. And inside the impenetrable cylinder, we have a magnetic field, pointing outside the page, say. So here we have a magnetic field, which at some point we are going to turn on. Okay. So the electrons can take paths which can go above the cylinder, or it can take paths which can go below the cylinder. And they can form interference patterns here, right? Okay, so is everything clear here? It's very similar to the previous, problem, except that now there is no outside cylinder. And the electron is still insulated from the magnetic field. All right, so when we turn on the magnetic field, before we turn on the magnetic field, the electron was free. It's not experiencing any electromagnetic potential. So the Lagrangian of the electron is just the kinetic term. Now, when we turn on the magnetic field, what happens is, because of the Lorentz force law, remember, the Lagrangian becomes half the kinetic term plus E by C, the velocity dependent term. Okay, I'm ignoring the electric field term because we don't have any electric field in this case, so phi can be taken to be 0. So when we turn on the magnetic field, the classical Lagrangian changes in this way. Do you agree? Hello?
Yes, sir.
Right. And then, so suppose that, let's suppose that, we take a very short path, and suppose we look at the, the path starting say at x n minus 1 at t n minus 1 and ending up at xn tn, okay? So when we turn on the magnetic field, the action that is associated with this path, let's call the action Sn n minus 1. That action changes, right? Because the Lagrangian changes, so we are adding a term. So that action changes by, so now the new action is the original action. Now the new term, this term, but this term has to be integrated over from the Tn minus 1 to Tn along the path. So dt times the velocity dotted with the gauge field. Okay, so this is very, very important to understand this formula. So do you understand this? Just compare with this guy, right? This is this term. And we're integrating over. Here, the x is the path. Okay? Any questions about this? Okay. So now look at this, this term. This term can be written as, so E by C, the integral is from T n minus 1 to Tn, d of t, d of x by dt dotted with a. So what we can now do is that we can use the chain rule and write this, transform this integral into a line integral, also known as a path integral, but for obvious reasons, we are not going to use that term here. We're going to call it a line integral. So it's an integral along some curve of the potential along that curve. Okay? Is this clear, what we have done here? Because dt dx by dt is nothing but dx. And here the integral is taken along the path that connects this point to this point. Okay, so this is the correction to the action as we turn on the electromagnetic field. So now let's take a path that goes from region A to region B. So according to the path integral, before we turned on the electromagnetic field, the contribution to the path integral would be this, would be all the actions that comes from subdividing this path into small bits, right? So I'm going to, write that as the product of all the actions that make up that path. But once we turn on when we turn on the electromagnetic field, what do we get? We get, of course, that contribution, the original contribution will still be here, but each segment of path contributes an exponential I times E by H bar C, a line integral, along that bit. But if we add up all the line integral, we basically get the whole path from beginning to end. Now there's something very interesting here, is that you would think that this second factor, the integral in the second factor, will depend on the path connecting these 2 points. But it turns out it doesn't. And therefore, we can take this second factor out of this product. So why is this independent? Because we know this from classical electrodynamics. x1, x2, if these are 2 endpoints, and we look at a line integral from this, between these 2 points, this depends only on the endpoints, right? It does not depend on what's in the middle.
Sir,
Right?
sir, isn't it not only in the case for functions whose curls are 0, but A is a function whose curl
Exactly.
is
Yeah,
1?
I told you everything. Yes. Yes. So what this is saying is that this is path independent. Sorry, I haven't told you the whole thing. This is path independent as long as the path doesn't cross a non-zero magnetic field. Okay. Okay, just 1 second, okay? And because in this path, the path that we are taking is a path going above, right? So it hasn't crossed the magnetic field, and therefore it is independent of the path. And this is very easy to prove. And so if we have, say, a closed path, so if I look at A dot ds, then by Stokes' theorem, what we can do is that, so this is the boundary of some region. By Stokes' theorem, this will be equal to the surface integral on the boundary of the curl of A dot, say, D of A, but this is nothing but the magnetic field, B. And now, if the magnetic field is 0, then this is 0. And therefore, if I look at this path, which say goes from here to here, and then say here to here. And because there's no magnetic field here, the integral is 0. And therefore, this path can be deformed to that path with the orientation changed, and the integral will remain the same. Okay, so these are the kind of argument that you have seen, for example, when you're doing contour integrals in complex analysis. Okay, so is this clear why this is path independent?